Hello everyone, my name is Roy Reyes and I'm representing Team 2 for Penn State's Masters of Software Engineering. For our capstone project, we decided to build Mars, a multi-UAV aerial reconnaissance system. Right now in Africa, poachers are killing off elephants and rhinos at an alarming rate, to the point where certain species are in danger of becoming extinct. The countries that help monitor the African savanna, which is about 5 million square miles, simply don't have the funds to purchase military-grade UAVs, high-definition satellites, or even just hire more rangers to help find these poachers. What we've built is a system which allows one ranger to monitor a large portion of land. We're using hobby-grade RC components, commercial off-the-shelf hardware that we put together, and we built ground station software that allows the ranger to command some of the hardware and get aerial data, which lets him take action when a poacher's in the area. So let's take a look at some of the hardware that we have here. The first part of our system is the ground station. The software for the ground station was written in C# and utilizes IIS and Microsoft SQL Server as a backend. It can run on any Windows 7 laptop. The ground station software connects to the transceiver, which is an XB commercial off-the-shelf component there, and it's used to communicate with the vehicles in the sky. It can view live GPS data as well as command the vehicles to take imagery to send back so the ranger can analyze the photos. The second part of the system is our quadcopter. Quadcopter is hobby-grade technology here. The technology of quadcopters has come a long way in the last few years. On the front, we've attached another XB unit. This unit maintains line of sight with our ground station software and simply hovers above the ground station. The only thing the ranger has to do in this case is get up in the sky and put it in altitude hold and position hold. And it'll maintain line of sight, so it'll always be in touch with the ground station and any of the vehicles in the sky. On the front here you can see our XB transceiver. This is a standard Arduino that is simply used to power and control it. If you turn it on its side here, inside there is a power module that keeps the XB powered and running. On the top of our quadcopter we have our flight controller. In this case we're using ArduPilot, GPS, and the various components of the quadcopter itself. The last piece of our system is the RC airplane itself. This is a standard hobby-grade RC airplane that's been outfitted with our system. On the front here is the Arduino Mega 2560 with an XB shield sitting on top and our XB transceiver sitting right on top here. This is connected to our GPS, which actually sits right inside in the cabin there. Because this EPO foam is transparent to GPS, we are not affecting the reception of the system at all. And we also are connected down here to our camera, which you will see right there. Utilizing the XB and the Arduino up here, the ranger, while the vehicle is in the sky, can command it to take a picture to send back to him so he can view it live on the screen and see if there are any poachers in the area. Right now I have our Arduino connected to a normal outlet, but if you open this up, a battery actually is going to sit inside of there, which Arduino connects to. This is actually the battery right here that will sit right in the cabin just like that, and it all connects through USB. Alright, this is Roy. We are out in beautiful 100-degree Texas weather, ready to get this flight in. I have the airplane here, it's all hooked up, ready to go. We got the transceiver and all the hardware components already sitting on there. The quadcopter sitting out in the field there. My brother's going to be flying that. He's going to get it up in the air and hover it there. Then over here we have the laptop. And I'm not sure if you can see it right now, but we are receiving GPS data. There's a timestamp going every second. And there's a transceiver connected to that. And so I'm going to hit record on the laptop so we can start recording the laptop screen. Oh wow, that's cool. This is all planned. Totally planned. I have to line this up with the perfect. And so we got the GPS set up here, and we're gonna get going. So I'm gonna fly. My wife's gonna hit the request picture, and we're gonna try and get some imagery down from the airplane. But more importantly, what we're gonna show is the mesh network. That's the whole part of this. So the range for these transceivers is not very far, and I did that on purpose for this presentation. I wanted to show the mesh networking aspect, and so with the airplane's going to lose range of the laptop probably by the time it's in the air somewhere around down there, like near the soccer post. And really, it's not, I think it's about 300-foot range. It's not much once the airplane's in the air. That's why we keep the quadcopter flying and level with the whole system. Everything is running at a 38,400 baud rate. That matches up with the actual camera itself. And then we have some error checking in there to help with the image capture and such. So, alright, let's do this. So, you take off, you'll be in the field. I'll take off from here and we'll get this going. I'm gonna do some checks real quick. We flew this yesterday. We flew the airplane into a tree. All right, Michael, you ready?
Yep.
Cool. Can you get a little more into the field then?
Yeah.
Cool, man. All right. Back a little bit to get a little more space to take off. All right, here we go. And we're in there. Fortunately, the winds are about 8 to 10 miles an hour today. So we shouldn't have too much problems with the airplane. We'll get the quadcopter in the air and then we'll get a picture from us. So we should still be getting consistent GPS data. Alright, Troy, can you hit a flash picture?
I clicked it.
Awesome. So right now the plane's pretty much already out of range of the ground station. And that's just because we've got the short range transceivers. If this were to be a real system, they actually make 28-mile range transceivers, which aren't that much more than what we paid for ours. But that would kind of defeat the purpose of the demo. Because we're using a lower baud rate, the picture's going to take a little bit longer to get here. Can you check the pictures here?
It still says receiving image.
Okay, cool. Flying the airplane further and further out. And as you'll see by the video that I should have next to this, when I actually put this video together, we will still be getting consistent GPS data. And that's because even at that altitude, even though we're not very high, we are, when the quadcopter is in the air, pinging off the quadcopter to the ground station.
So there's all the squiggly letters and now there's a space and it went back to the GPS coordinates.
Perfect. So the reason it does that is when you hit request GPS data, the plane will stop sending other data to give the ground station time to prepare itself to receive the image. The ground station uses that information to clear its buffer and then set up cameras to get ready for the image. Can you hit, oh, I tell you, can you hit request picture again?
Yep.
Try and get a picture of us down here. Get ready. Alright, now. You do it?
Yep.
Awesome. I'm going to bring the plane back in. Michael, you can bring the quadcopter down.
Oh God.
Plane came down in one piece. That's a good landing. That's a good landing.
That's a good plan.
So now that the flight is over, let's take a look at the software that we use and some of the data that we got from the flight. First off, here we have our ground station. This screen right here is the comm settings tab. This allows you to connect to the transceiver that connects to this laptop using USB. Once you open that port, data starts getting streamed onto this little console here. You can see I have some flight information from the flight from earlier. And when you're connected, these buttons actually become enabled and let you communicate with the airplane itself. We also have an audit history button here. This lets you go through and see we have history from a few days ago, actually, before I cleared the database. Or rather, after I cleared the database. and it just lets you view all the commands that were sent back and forth between the airplane and the ground station. This tab is the aircraft status tab. What you're seeing here is the latest imagery requested, and I'll explain in a second why this image didn't come through correctly. And a GPS map, we're utilizing the Google Maps API here, so you have the same functionality that you would have in normal Google Maps. And this vehicle moves around as the airplane is flying. Now, and down here you would also see some summary information for the current vehicle. Now let's talk about this image. Why is this image jumbled up? So, as I was flying, the very last flight, and unfortunately I didn't get this on video, the plane went down. I lost all stick input, and the plane is fairly well balanced, and so it pretty much glided down to the ground. It hit the belly, but the rear landing gear was torn off, and nothing too major, nothing I can't fix. As I was walking to it, trying to think of what happened, why did I lose all input, I noticed that there was a a water tower near me. On top of that water tower was a radio tower, probably a cell phone tower. And I didn't see that before. And cell phone towers emit a very strong signal. And when I was flying in the area, I'm fairly certain I flew directly in the path of that signal. Now, why am I bringing that up now? Well, that signal puts out a lot of noise. And so when we transmit GPS data, for example, and I'll show you what that looks like in a few seconds, it's a small string. Hard to get jumbled up because there's really not much space that it's taking up. An image, on the other hand, takes about 30 seconds to 45 seconds to transfer, and at least at the frequencies that we're using, the transceivers we're using. So in this case, what's happening here is we're transmitting a signal for the image. The radio tower is putting out signal for cell phones, and the ground station is doing its best to put everything together in a way that makes sense. So not much we can do about that besides find a different flight area. But one thing that I want to point out about this software is this is a C# application. I have actually the code back here because I like to run in debug mode. But this aircraft status screen is actually a web app. So we just have a web browser viewer here that loads a local host, which is running IIS and SQL Server. And the reason we do that is, and here it is in my actual browser. The reason we do that is any computer that's on the same network can view the same information that an operator is viewing. Now, they can't command the vehicle. We want to leave that for the operator. That's why the send picture command was on the other screen. But they can view a status. So if you had multiple vehicles here, you would be able to zoom out, see them all, and do whatever you need to do without affecting the actual airplane. And you can see the latest imagery data coming in. So on that note, let's look at some of the data and see what it looks like. So I did 2 tests. Well, I did more than 2 tests, but for this final one, I did some 2 tests. The first one is with no mesh network enabled, so it was just the airplane and the ground station, and one with the mesh network enabled, so the quad was in the air and flying. Let's look at the no mesh network first. So this part, the timestamp here is put on by our logger itself, and you can see, here's at 4 o'clock, 4:07 and 25 seconds, at 43 seconds, at 51. There's no consistency here. And that's because when the plane takes off, it's almost instantly out of range. The reason that's the case is for the sake of this demonstration, we want to demonstrate the mesh networking concept. So we got low power transceivers. And we did that because we want the plane to have to go through the quadcopter to get to the ground station so we demonstrate that it works, right? And so these signals are not that great. There are a couple times in this case where you see this packet's all messed up. There's a packet inside of a packet inside of a packet. And it's not clean. Let me show you what it looks like when the mesh network is enabled. Much more consistent. Look at the timestamps now. 17 seconds, 18, 19, 20. I'm willing to bet the biggest gap we had is probably 2 or 3 seconds. Let's look at the packet itself while we're in here. So ignore this front part. Actually, let's do this. There we go. So for this project, we have to come up with a definition for these packets. So the ground station can talk to the airplane and everybody was cool. So the first 6 bytes identify who the packet came from and what it is. So in this case, the packet came from PL1. So this means this packet came from plane 1. The next 3 bytes say what kind of packet it is. It's a GPS packet. And the other important information is this comma tilde exclamation point, which signifies the end of a packet. That's how our ground station knows I've gotten all the data I need. Because really all the ground station is getting is a stream of text. and it's up to the parser that we built to decide when that's a packet and when it should send that on. So this is how it knows that we've received a packet. The data that we want out of this packet is right here. This is called an NMEA, November Mike Echo Alpha string. This is data that comes pretty much directly from the GPS sensor. This is a common format. And we decided to send this data to the ground station because we want the ground station to parse this. The reason that is there's just a lot more processing power down on the ground. We don't have to waste our power and CPU cycles in the air trying to parse this string. And it's not a very large string. And you'll notice that when the network was strong, there weren't any of these broken up packets at all. So if we go down, you can see the timestamp's pretty good. These are just heartbeat essentially from the airplane. Then we get to here, GS1 PCT PL1. So if we think back to what I said earlier about our packet definition, first 3 bytes are where it came from, ground station 1, PCT. Next 3 bytes are the command, picture take. And in this case, we want to say who should be taking the picture, PL1. So this packet was sent from the ground station, GS1, to the airplane, PL1, and it told it, hey, take a picture. So the airplane received the command, parsed it, and told the ground station, hey, this is plane 1, PL1, right? BFC, clear your buffer. And what it's saying there is, get ready, I'm about to send you an incoming picture. And then about a minute later, the picture was completely received. So the plane actually gives the ground station about 5 to 10 seconds, actually I think it's 5 seconds, to empty its buffer and get ready to receive an image. And we do that because we're sending this massive image. We want all the processing power focused on what the ground station is receiving. So PL1 from plane 1, PCR picture received, and this is a string representation of hex, or the image itself. Now you can tell it's a JPEG because it starts with FFD8, which is just a hex indicator. It's the beginning of a JPEG image. FFD9 is the end of a JPEG image. Our ground station takes this string, converts it into bytes, and we get our JPEG. So then we go back to sending GPS information, heartbeat status, and you can see pretty consistent. And I'm gonna keep scrolling down here. And then remember, this is when the mesh network was on, so we got good data here. Some looks like right here, some broken up packets. That's all right. Our ground station can accommodate for all that. Here's another command telling it to take a picture. We got that command. Clear your buffer. Picture received. Now this was a malformed picture. So you see we start off FFD8. So we got the beginning, but there's no FFD9 at the end, which means this packet was broken up at some point. And I wonder if, yeah, this is a really broken up packet. It's missing a lot of data. But there's one below it here that was also broken up actually. This probably all goes back to that cell phone tower that I was talking about earlier. And then going down, we see more and more data here. So no mesh network, pretty bad, nothing really to show for itself. Good mesh network, pretty consistent packet data. What we can translate that to is Google Earth KML files. So you can see my flight here. This is about, I guess, a 14-minute flight that I flew. And you can see this was when the mesh network was on, so it was able to capture my flight path, and I guess Google it merges some of the points so it doesn't have as long of a path. Here's what happens when we put the no mesh network one. Not even enough data to make any sense. I mean, it's clear it's 4 minutes of flight, but it can't make anything out of it because it was all pretty malformed.